Working with Data Arrays, Part 2.
The very first subject that we addressed were the file instructions. But before we got into in particular, the file shift instructions, we talked about arrays. This particular family of instructions, referred to as shift instructions, as it is with all instructions, they address elements in the controller's memory, each instruction having a unique effect but similar in type. All of the file instructions have a unique effect, but they're very similar in behavior. B for bit, F for file type instructions, affecting the state of bits in a word or file. We're going to start this volume, as I said, with the bit shifting instructions, and then file shifting instructions later. One of the subjects we did not cover in Volume 1, the beginner, the subject of arrays. We've not really worked with arrays yet, so let's start there with arrays. Arrays, single dimension, or you could say a field of bits. And we had you open RSLogix 5000 from the Start menu, or from a shortcut. We had you start working with arrays, but I'm going to step aside for a minute and talk about arrays from another perspective. In front of you, I have RSLogix 500 and I have RSLogix 5000. If you are a learner who does not know 500 at all, then this is totally unfamiliar to you. But these are the graphical user interfaces for the old development environment and the new development environment. They're very similar, even though if you're new to this, they don't look similar, other than you see something over here that looks like something over here, and then these two areas here look similar. If you look up above here at the menus, you see some slight similarities, but other than that, they probably don't look that similar to you. But the thing in particular that we wanted to talk about was arrays. In this project, the one that you're actually going to do, there are no arrays yet. We did title it L35E arrays because I'm using an L35E processor. That's the name of the first lab project. But let's look over here at RSLogix 500. In RSLogix 500, you had to accept predefined variables, whereas in 5000, the only pre-configured variables are those for module define, which would be these right here. These are the classes of objects, which we discussed in Volume 1, the beginner manual, and then we instantiate those by assigning them to a slot. In our controller tags, we have local, slot 1 and slot 2. See down here in slot 1 we have DCN6 relay out 4. There's our inputs and there's our outputs, and then we have a combination analog card. These two sets of tags right here, local 1 and local 2, they are instantiations of these module defined types here. You do not have that in a SLC 500. Whereas down here we have I/O configuration, and it shows a tree, so to speak, and if you want to add more modules, you right click, new module, and go pick a module. Over here, the I/O configuration was a completely different proposition. And then you could read I/O configuration. That is very similar over here to discover modules. Now, this processor here does not support discover modules. But with the SLC 500 family, if you were online with it, you could read I/O config because it would go through the communications port, through the processor, out onto the active backplane, and then it would go down through each slot to see what was in there and then report back to you. So configuring your I/O is really simple if you were online with a SLC 500. The point I'm getting to here is I'm comparing the two, what you see here with what you see here. The thing of real interest to us is not output and input files, but all the other files. And I'm going to pick on the simplest, B3. I'm going to open that up, and that is a 16-bit or an integer data type. And it is a pre-declared variable, B3. The :0 implies that it is an element of an array. I could go to properties of that file, because all of these B3 through F8, and by the way, you can have 9 through 255. You can create more data files of these types: binary, timer, counter, control, integer, and floating point. We call it real over here in 5000 land. All of these, you can increase the number of elements in the array to a total of 256. So you see here I have B30, and that is all I have. If I go to properties, then here I say one element. If I say 2 elements and apply, now you see I have 2 elements, B3, word 0, word 1. I now have an array of 2 integers. And the name of the array is B3, B3 colon 0, B3 colon 1. I can put in 256 here, or I can put in the highest element that I want. I'll just put in 256, and now you see if you scroll down, you have 0 through 255. So the name of the array is B3, and then the element or the integer is 0 through 255. And then we had timers. You open that up, you see there's one element in that array, although that timer data type is made up of 3 integers. That is a data type, but in 500 land we did not call it a timer data type. Literally it is just 3 integers, but they are set aside for the first element in the array, T4. And of course C5 for counter, and those are also 3 integer elements of that array, but there's only one. We can go to properties and say there are 3 of them. Now we have C5 array, element 0, 1, and 2, and so forth with integer and floating point. I just wanted to introduce you to arrays by showing you what we had in one of the earlier platforms. And by the way, this is RSLogix 500, which programs, it's the development environment for SLC 500s and all of the MicroLogix. MicroLogix 1000, 1100, 1200, 1400, and 1500. All of those processors are supported by RSLogix 500. This is the older software. Arrays are not new to you if you've used this older software. And by the way, RSLogix 5 also looks very similar to RSLogix 500. The I/O addressing is a little different, but everything else is extremely similar. Let's minimize this in case we want to come back to it for comparison and maximize our RSLogix 5000 graphical user interface. This is where you're at in your manual. I had you open up the controller tags database to make sure that you have your I/O down here. These 2 modules under compact bus local are represented here by these instances of these module defined tags. Something that I wanted to show you, you see it says beginner plus L35E. That's the name of the processor, not the name of the program. Up here is the name of the program. It has arrays in it. But let me show you something about that processor name. You can go to controller properties here, or you can go to controller properties over here. This is the easiest. I can change the name. I can make it L35E Monkey Shines. Now you see down here it says L35E Monkey Shines. The point is, if at any step in your learning process, if you don't like the name of the processor because you accidentally named it something that is distracting, go change it. It's easy to do. Now I had you open up the program tags database by double clicking there. And by the way, just to refresh your memory, whatever is in this space right here, we'll call this the workspace or the palette, you can close those one at a time because they are all stacked up. Now if you want to see what's there, you can go to Window, and it'll show you that you have the controller organizer. That's this item right here, and then you have the main program open, you have controller tags open, and you have program tags open. If I want to switch to controller tags or main program, all that I need to do is to click on it from Window. Now there's nothing in the main program. However, you can also close them here with this small X. That's the controller tags, and now we're back to program tags, and if you go up to window, you see that's all that is there. Now you can close this too, by the way, and then you go up there to you can turn it back on, but you can close it from there. Typically, I advise to leave this here in the beginning. There'll come a time when you really don't go back over to the controller organizer very often for anything, simply because you're having at it in your programming, and there's nothing over here that you need. Remember, all of this data types here, these are classes of objects. You can't do anything but look at the template. It has no effect whatsoever on actually doing programming. That's all up here in your instruction set. I had you create a tag in your program tag database. I had you name it any array. The data type is a dent. Any array, we named it that to demonstrate that the name is irrelevant. It could be any type of array, and the name array does not have to be in there. To remind you what this tag is, it's just any old array. And it could be any one of any of these data types. I cannot think of a reason that you might make any of these an array, but the dent or the Boolean, I can. Or timers, counters, the basic data types. The dimension, and notice it shows 3, dimensions 0, 1, and 2. Well, if your dimension 0, your base dimension, if that's 0, well, obviously there can't be a 1 and a 2. That's why they're grayed out. I'm going to make this 10, which I told you to do, and notice that instantly dimension 1 now appears. If you have a dimension for the array for dimension 0, then you can have a dimension for 1. And if I change this to something, now you see dimension 2 pops up. As long as I got off the subject here, that is a 3-dimensional array. We're going to cover this much, much later in the volumes. Think of a 3-dimensional array as such. A single dimension array, so we'll back up here, we'll make this 0 to see if that gets rid of both. Yes, it does. A single dimension array of 10 double integers are 10 contiguous memory locations. In other words, it's 10 32-bit memory words all in the exact same spot in memory. They're contiguous, one after the other. You could also look at that as a row of objects. If you picture out in front of you, whether out in front of you on your desk, and we'll just do it that way, in front of you on your learning surface where you're sitting, picture 10 cubes, 10 white cubes, 1 inch by 1 inch by 1 inch. They're objects. That is an array of 10 cubes. 10 cubes out in front of you in a row. A single dimension array is like a row of objects, in this case 10 objects. If I add another dimension, and let's say that I say 2, now I have 2 rows of 10. I have a row of 10 right in front of you, and then right behind them another row of 10. So I have 20, but I have 2 rows of 10. If I make this 10, now I have 10 rows of 10. And as you picture this collection of objects in front of you, it is a collection of white cubes, 1 inch by 1 inch by 1 inch. It is now formed a square that's 10 by 10. You have 100 of these white 1 inch cubical cubes, these 1 inch cubes, right in front of you. That's real easy to see. A row or a group of rows that form 2 dimensions. Width is 10, and now the depth, we did 2 first, now we did 10. You can picture that. If I now make this 2, now I have 2 of those 10 by 10 structures, one on top of the other. So now it's 2 deep. And when I look at my structure in front of me, I see that there are 2 layers of white cubes, and each layer is 10 by 10. If I go to 10 for the 3rd dimension, now I have 10 layers, and each layer is 10 by 10. Well, I didn't mean to get so far off the subject discussing what 3-dimensional arrays are. We only wanted a single dimension, 10, and there we have it. If you were online right now, you could still change this. See, the cursor's still up here. But if I hit enter, or if I click someplace else, that's done. Now we're offline, so we can change it. But if we were online, you'd have to delete that, and recreate it with the changes, or you would have to save, go offline, change it, make your edits, save, and download. Just a little reminder. Okay, I had you open up this any array, and you can see there's your 10 elements, 0 through 9. And they all show as double integers. Then I had you open up any one of them, doesn't matter. And now you see each one of them is made up of 32 Boolean, 0 through 31. You have a field of bits. Even though this is a single dimension array, there's two ways of looking at this array. If you look at it in your mind as 10 32-bit integers, double integers in memory, then you know that memory is an actual physical object, and it's called a memory array. And the array is 32 bits wide. If you look at these 10 double integers, they're contiguous, and let's say it's laying flat, the memory chip is laying flat on the desk in front of you. The row closest to you is probably any array 0. It's the first element, and then right behind it is 1, then 2, then 3, then 4, 5, 6, 7, 8, 9. That is 10 double integers. You have now formed a field of bits that is 32 bits wide and 10 double integers deep. But really, the only dimension that counts is the actual double integer, because if you were to create a Boolean array, that would look completely different. We'll just do that. That's not part of the lab, but we'll make this a bit array, and we'll go over here and define it. Now, you don't have to click here and drill down. You can click here. So it's reverse video, dent, type in B-O-O-L, pops up, hit enter. Okay, now, that is not an array. I hit enter demonstrating something, so I'm going to go back and edit this, and we'll make it 10 to begin with. We have an array of 32 Boolean, bit array 0 through 31, and they're each Boolean, but there's nothing more to expand. Really, there's no difference between this bit array and one element of this array. That's 32 bits, this is 32 bits. However, if we edit this and make it 320, now these two arrays are the exact same size in terms of access from your program, but they are not the same size in memory. As a matter of fact, when you create a Boolean tag all by itself, it occupies one dent in memory. Dents are the native data type for the Logix engine. If you create a Boolean tag, it is bit 0 of a dent, but you can't see that. In other words, when you create Boolean, it just doesn't find an empty spot in a dent somewhere to throw it in there. It uses up an entire dent to create a tag that you only have access to as a bit. This 320 Boolean tags now takes up the same memory as if we expanded this out to 320 dents. Now they're equal memory space. If I change this to 320, I'm not going to do that. Right now, with this 10 and this 320, both of these occupy the same number of memory locations bitwise. This in 10 double integers, 320 bits, or this as an array of 320 Booleans. So obviously you can see you don't want to do this business right here. So I'm going to delete that. I just wanted to clarify that. That wasn't in the lab, but why not talk about it? I had you expand any of the 10 words exposing the 32 bits. I asked you how many bits are in those 10 dents. Well, I already told you 320 bits. Are the bits contiguous? Yes, they are. That's something else I wanted to point out. Physically, in the memory array itself, the physical memory chip, these form a surface area, a rectangular shape of bits, at the microscopic level. But you can treat these as contiguous bits in a sense. If you start at bit 0, we'll say if you start at bit 31 of that element 0, you can treat that bit as the next bit after that bit. So 27, 28, 29, then bit 0 of element 1 and so forth, all the way from element 0 through element 9. You can treat them that way as if that's how they exist. especially, and only I guess if you're working with file type instructions, especially bit shift left and bit shift right, which are the instructions that we're going to get to right now. Now in the manual I did show you a graphic that I created of the field of bits. It is a single dimension of dents, but when you consider the 32 bits in each dent and correlate the relationship of any bit in a dent to any bit in any other dent in this array, it provides you a two-dimension array of bits to work with. If you were trying to identify the presence or absence of something in the real world that actually occupied one of 320 positions in a rectangle like this, you could use ones and zeros to represent the absence or presence. You could treat this as a two-dimension array of bits. That wasn't the intent with the word array. It's the number of elements of that data type, which is dents. Any bit instruction can address any of these 320 individual bits, and any word instruction can address any of these 10 individual words, and any file type instruction can address any group of words, any two or more words within this 10 dent array, given that the size and boundaries are respected in how you configure a file type instruction. In this exercise, we are just going to be working with bits, but we wanted to cover some of that territory while we were in front of you. We named it any array, as I explained, just for that reason. It can be any single dimension array that you like. Don't concern yourself with 2 and 3 dimensional arrays. I gave you enough of a preview that it should satisfy curiosity somewhat. Then I had you save your project as beginner plus L, your processor number, arrays. Now, a little hint or advice, you can name your files anything you want. You can make them BP, L processor number, arrays. You can name them anything you want. Putting 00 after this one and increasing that number all the way through this manual, whatever the name of the file, will allow you to find the order that these are in. Save your project and go offline if you are not already offline.